Hi everyone, thanks for coming to my talk. Apologies for not being able to attend in person. Instead, I'm recording this from Canberra, and for that reason, I would like to pay my respects and acknowledge the Ngunnawal and Ngambri peoples, who are the traditional custodians of the Canberra area, and pay my respects to their elders past and present. Today, I wanted to give you a primer on elliptic curves, what they are, and on a series of contributions that I made last year to OpenSSL, which is undoubtedly the largest crypto library, and almost certainly runs on the majority of your devices and all of your servers, as well as a discussion on some relatively low-hanging changes I managed to make to one particular elliptic curve, and how that saw roughly 6.6x performance speed up, and how that could be attained. For those of you who've likely interacted with cryptocode, I have reason to doubt that that was a pleasant experience. Cryptocode can be extremely obfuscated. One of the inherent difficulties with understanding cryptography code is that it's cryptic. The properties which we often desire out of our one-way algorithms like hashes or our two-way ciphers or our pseudo-random numbers is that they obfuscate the original data in a particular way. It's little wonder then that cryptographic code itself can be highly obfuscated, even if unintentionally. The underlying mathematics is almost maximally abstract, and it'll often wield a lot of the gifted and talented concepts which you might come to expect from a crypto CTF. Things like prime numbers, permutations, and in the case of elliptic curves, even allusions to geometry and maybe even calculus. Coupled with the complexity of the mathematics is the code itself, which very, very often is filled galore with single letter variable names, and for performance reasons, because loops can often be unrolled, often random indices as well. There's no escaping index hell. And often the only documentation for one particular implementation in OpenSSL is its implementation in another crypto library, and often that documentation will simply be a link to a paper, a mathematical paper, and the link might be broken. That's all pretty typical. In my experience with crypto code, the algorithms themselves are so complicated that if I wish to adapt one particular routine, what I do is I write my own reference implementation using no cleverness at all, and then once I've got parity with correctness, only then do I kind of atomically update, iterate, see if it works, see if it improves performance, etc., etc. So the optimization process can be very extensive. What makes cryptography performant? What goes into performant code? Well, perhaps the only thing that it can be worse than deliberately obfuscated code is code that's written for performance. I think that's fair to say. At least in cryptography, in opposition to many HPC applications, thankfully the algorithms only tend to operate in discrete mathematics, and what that means is you're very unlikely to touch a floating point number. That's a small consolation. But where we have an exact call for results, and we're dealing with very, very, very large integers, I mean, it's not uncommon for them to be larger than the number of atoms in the universe, let's say, you invariably have to use some sort of large integer type. And yes, with large integer types, you can no longer account on a single multiplication, for example, being O1. I mean, obviously it depends what you define to be O1, but typically multiplications expect them to be expensive. Not only that, but you've got to be wary of side channel attacks. This is an additional pressure with crypto code. In short, no choices of random number or no choices of key should at all be able to influence the runtime of your calculation. If that is ever the case, a real pitfall is that a choice of key, sorry, beg your pardon, the runtime of your program might imply properties about your key, which becomes problematic. And so to add just more complexity into the mix, crypto algorithms, it's not uncommon for them to throw in extra and seemingly superfluous work, whose results will in fact be disregarded to avoid variable time execution. It's as if there's a sensible way to write things and a cryptographically secure way to write them. And so, yeah, this is a good question. Should we roll our own crypto? Should we or should we not? I would insist no, but also that's what I've just been working on. For all these reasons and more, I don't suggest that you roll your own crypto. The simplest and most common misuses, again, not quoting any stats here, of cryptography, they happen through simply mishandling the data, mishandling keys, etc., exposing secrets in software. When implementing the actual core arithmetic, any bug at all, however rare it is, opens up problems for replay attacks or similar. Any implementation bug at all, can drastically lessen the security of your algorithm. Cryptographic algorithms simply handle such truly massive numbers that the following example becomes relevant. So this is a comment taken out of a related algorithm, a related curve to the one I was working on. This is SecP521R1, and yeah, don't have to read a lot of it, but about midway through, you'll see this horrifically long hex number. Yeah, so it turns out that under exactly that condition, where one of the internal values into the program is equal to that, under exactly that condition, the program can be variable time, which could, if you got your tinfoil hat on and you're paranoid, expose some sort of timing side channel. And so there is in fact a test case in OpenSSL for precisely this number, which we're pretty sure is the only one that's affected. These sort of bugs matter in crypto. Yeah, but let's now talk about what an elliptic curve is. So you might have heard some other cryptography algorithms, for example RSA. If you administer a Linux server, then it's highly likely that the SSH session which you have, you'll authorize with an RSA certificate. So yeah, RSA operates off prime numbers, and the RSA sort of forms the base of what you might expect to see in a crypto CTF. But in spite of elliptic curves actually being similarly adopted for many of the same applications, it's actually substantially less likely that the people will understand ECC. At its core, though, ECC and RSA can really be thought of as equivalents to a limited degree, in that they're both asymmetric ciphers, which ultimately rely on some sort of discrete logarithm problem. So in RSA, the fast side of encryption, when you perform the encryption, involves repeat exponentiation. So sorry, exponentiation through repeat multiplication, and so does the decryption side. But implicit to the security of RSA is that inverting that exponentiation, which is to say taking a logarithm, is complicated. We call this the discrete logarithm problem, because what needs to be done is to compute a logarithm in a modulo ring, which we'll discuss about later on. So the crux of it is that exponentiation is quick, but inverting that exponentiation is slow. And so even while elliptic curves have been a standard for some time and are in fact the preferred algorithms by the NSA as well as other authorities for digital signature generation and verification, there's still this aura of mystery around them because, well, I mean, I would suggest likely due to the name. So the image on the right is an example of an elliptic curve. It can look a bit different to that. One thing you'll notice is it's not an ellipse, but instead this curve has interesting properties to do with its roots. So it's a polynomial curve that the expression I'll get into later, and the points here, it looks like we're in the real plane, or in reality more like the real projective plane, but in reality we can replace the reals with any field f. So we're in the projective plane in some field. I'll get into what a field is later. But we want to come up with a sort of discrete logarithm problem. And so what we do is we define this operator. So the points, the numbers as it were, our number system operates on points on the elliptic curve. So suppose this is a point A and this is a point B. You'll notice that the line connecting A and B, I'm going to crudely draw this, sorry. The line connecting A and B is a chord. It's not a tangent to the curve anywhere. And so we define the addition, for reasons, to be, so Bazou's theorem requires that the third intersection be this third point on the curve here. So the third intersection must exist. By convention, sometimes 2 points can add to infinity, which is an interesting caveat, but in this case, here's the third point. And we define the sum of 2 points A and B to be the reflection in the x-axis of that third intersection point. I'm going to call intersection points from here on out roots. This works for A and B, and B plus A is actually going to produce the same result. Why? Because we're going to get the same line, right? And so the same roots. What about now if we take a point and then we take its tangent? So Bazou's theorem tells us, applied to this particular polynomial intersections of the line with this particular series of curves, says that tangent points, let's call them C. The tangent of a point C is guaranteed to have exactly one other root, which could possibly be infinity. In this case, it's this point here. So let's take its reflection along the x-axis, and we define this point here to be 2 times c, to be c plus c, as it were. Yes, so this looks like an inherently geometric expression, but in reality, the a's, the b's, the c's actually can sit as points within a projective coordinate system in an arbitrary field. What actually is a field, though? Right, so a field is a sort of algebra, a sort of algebraic structure. The elements of that field are these number-like things, so I'll call them field elements. Critically, you can think of a field as a sort of mathematical construct which has all the algebraic properties of the reals. It has addition, subtraction, multiplication. Non-zero elements also have a multiplicative inverse, and so off that you can define division. There's no such thing as zero division still. And you have your identity. So 1 is the multiplicative identity, 0 is the additive identity. So yeah, so think of the reals without necessarily the order or analytic properties. Critically, the fields which we care about here are what are called finite fields. And more specifically than that, we're going to construct fields from modular arithmetic, modulo a prime. So what's modular arithmetic? Yeah, so you know how to do division over integers. Not all integers divide evenly, but the long division algorithm, which we're familiar with, always guarantees some sort of remainder. So modular arithmetic, just as a refresher, is you do normal arithmetic over the integers, but at some stage before producing a final answer, you take a remainder, modulo a prime. That is, you take your prime as the quotient, and then you output the remainder as the final sum. And you actually get the following arithmetical properties as per the real numbers. However, we lose all notions of order. So the class of numbers with a remainder p minus 1, for example, suppose our prime is 7. Then the number 13 has remainder 6, but the number 14 has remainder 0 by convention. So it's clearly not even an ordered set. Nonetheless, the addition and doubling, which we were talking about earlier, still carries through into arbitrary fields. Irrespective of the field, we still get a notion of addition and doubling, because that's actually not a result from geometry or calculus, as it turns out. It's actually an algebraic result, an algebraic property of the curves we've chosen. So how do we get our discrete logarithm problem? Well, intro a pretty tragic problem with our conventions here. So the forward step, which is meant to be fast, is point multiplication. That is, for some generator point on the curve p and some natural number n, do enough repeat additions and doubling in order to get the n times multiple of p. As you can imagine, a sufficient way to do this is you start with an identity, which is points at infinity, which is a caveat of our number system here. And if we repeatedly add to that point our generator p until we get np, then that's our notion of exponentiation. And then for a particular np, where n is secret, determining n is like taking a discrete log, as it were. So yeah, we get a discrete logarithm problem. But when your tools are addition and doubling, which are constant time in and of themselves, the problem is the choice of n may well dictate the sequences of additions and doubles you want to do. And to avoid timing side channels, you better ensure that the sequence of addition and doubling is statically determined at compile time, and it's got to be constant for every choice of n, because yeah, at that rate, yeah, exponentiation or point multiplication in this case is particularly sensitive to timing side channels. N is assumed to be a random nonce, for example, in the signature algorithm, and so it's really critical that our code isn't susceptible to timing attacks. However, we do still want this to be fast, even while we're going to have to do some redundant computations in order to blind against timing attacks. And so when it comes to optimizing this code, the crux of it is simply to optimize the underlying arithmetic. And so we can actually discount and not have to think about multiplication in as much as you can treat it as just repeat application of addition and doubling, which is itself implemented in field arithmetic. And so let's build our way up again. So we started with an elliptic curve. So a curve is some polynomial equation of the following form. And the a's, the b's, the x's, and the y's are all in our choice of field. So in our particular case, that's going to be a prime. Modular arithmetic with a prime. And that from that curve, you get a discrete log problem. And from the discrete log problem, you build on top of it a key exchange algorithm. So there's a variant of Diffie-Hellman for elliptic curves, as well as a signature generation and verification, a sort of DSA. However, when it comes to performance alone, we just care about the field arithmetic. And so I've coined that there are two possible choices of strategy when it comes to field arithmetic. You can either exploit the specifics of the prime which you've got with a Salinas method, or you can use a more generic approach with Montgomery reduction. We'll get into more of that in a sec. So this is our algorithm which we're working on. It's called SecP384R1. Sorry, it's not a very memorable name. It's actually the NSA recommended algorithm for key exchange and digital signatures at the moment. So there are larger key sizes than P384, but it's the middling one. So the curve is defined by this lovely bit of algebra with constants 3 here and some enormous arbitrary constant there. And those are both set by the NSA. And our x's and y's fall into a particular field, which is arithmetic modulo P384. So for the remainder of the talk, the exact makeup of this prime is what's relevant. So P384, as you can see, is going to be a 384-bit number. And it's going to be just slightly smaller than 2 to the power 384, as you can see. And it's going to have a lot of contiguous runs of 1s and a lot of contiguous runs of 0s, as you might be able to infer. As you might imagine, objects in FP384 are liable to be very large. So since the prime itself is 384 bits, the majority of numbers, in fact half of the numbers, are going to themselves be 384 bits in bit width, which has some substantial complexities along with it. So we don't have any 384-bit wide registers, so we're going to have to split things up into the most common way to do this in crypto, or in any large integer library, is to split up the kind of place values of a number into what are called limbs, but we'll get into that in a second. So yes, so we begin with numbers which have a bit width of about 384. That's the minimum number of bits required to store them. But from there, we want to do some arithmetic. So suppose we add two similarly large numbers, and the numbers are both, well, non-negative. I mean, without loss of generality, they can be non-negative because we're in a modulo ring. Then if two numbers have bit width n, then after addition, their bit width is going to go up by 1. That is, the size of the operands could potentially double during the addition. Subtraction is interesting. So we want fast subtraction to be possible. But as you might remember from the long subtraction algorithm from primary school, what happens when a digit above is less than a digit of the operand we're subtracting away, then you have to do what's called a carry. If you don't do a carry, if you want to cut out the carry logic and make this all run fast, then you run the possibility of underflow. So subtraction has some unique complexities to it. What about multiplication? Well, addition arithmetically increases the bit width of our numbers. Multiplication actually, as we'll see, geometrically increases the bit width, so it's much harder. And then multiplicative inversion in a modulo group is especially complicated. The easiest way to do it actually is to use Fermat's little theorem, which some of us, if we're familiar with RSA, will be familiar with. But in short, that it requires a big exponentiation, up to nearly the size of your field. So that's a difficult, substantially more difficult than the other operations, but not too difficult still. Interestingly, you'll implement inversion in terms of multiplication. Lastly, we have modulo reduction. So we just said that we're going to have to store these numbers in terms of large numbers of limbs, representing the place value of the number. So the trick with modulo reduction is that, the primitive algorithm is to divide by the quotient, which is the modulus our prime, and then discard how many times the prime goes into our number and only return the remainder. That's an inherently iterative algorithm. And so not only is it liable to be slow, we also can't introduce any variable time factors into our code. So modular reduction is hard. Yeah, why would we want to do modular reduction? Well, forgetting timing side channels for a sec. So to begin with, if you let your numbers get too large, then arithmetic on those numbers starts to become expensive. And if you don't do reduction at all, but if you reduce after every little bit of arithmetic, then you'll also tank your performance for different reasons. So there is a kind of intelligent choice which needs to be made as to when you do that. Just a refresher on how integers grow. So suppose we have two numbers a and b, and we take their sum. So a is bounded above by m for Mike, b bounded below by n for November. Then a plus b is less than n plus m. That's actually the minimum upper bound, which I can put on these two numbers. Is that right? Yeah. What about multiplication? Well, yeah, if the same bounds for a and b, then ab is bounded above by nn. That's pretty close to the minimum upper bound. And so, yes, we run into problems here. As you can see, yeah, the bit width for addition grows arithmetically, but for multiplication it grows geometrically. And yeah, you run into this problem that the instances where you do modular reduction better be statically known, or else we've got a timing side channel. Yeah, let's talk about why multiplication in particular is hard. Well, let's jump into some code for that. Sorry, wrong code. Nice. Philem ref. Okay, here's some beautifully obscure crypto code for us. So what this is doing is this is computing a lim of the product with place value 0. And the way you get, so we have operands, input operands, which are arrays of limbs in 1 and in 2. And each of them have place value 0. And we're going to multiply the place value 0 limbs together, which were 64-bit types and are now being promoted into 128-bit types. Because two 64-bit numbers, their product is going to be 128 bits at most. And so in order to produce the output lim with place value 0, you multiply the zeros and zeros. To produce the output lim with place value 1, you do 0 of the first term times 1 of the second term, 1 of the first term times 0 of the second term. So the place values add together into the resulting place value. If you alongside this, if you're doing the long multiplication algorithm learned from primary school, then this sort of intuition matches up, right? Lastly, we get to outputting the fifth lim, for example, and we see that we actually have a sum of 6 different cross products as well, 6 different cross terms. So suppose each of these limbs is going to be a 64-bit number, and so what we're doing, we're summing together 6 examples of the products of two 64-bit numbers. Two 64-bit numbers can have a 128-bit product, but that actually doesn't leave us any room to sum together any 128-bit numbers. And so we better actually precondition these limbs to be smaller than 64 bits in order for this calculation to not overflow. These are just some of the inherent complexities to doing multiplication efficiently. There have got to be bounds on our input variables, on the input sizes of our limbs, and multiplication inherently increases the amount of data we're going to have to store. So the resulting type, for example, has 13 limbs, whereas the inputs in this example had 7 limbs. Yeah, multiplication is hard. And so since it's necessary to repeatedly, after a multiplication, you might only just have enough bits remaining to do maybe a couple of additions and a subtraction. And so soon after you've got to reduce. There are 2 approaches for reduction. There's a Montgomery approach, which we won't get into here, but it's actually the baseline approach which OpenSSL uses. It provides a generic implementation for every choice of prime. We'll just briefly discuss it more in a sec. Or you can use the Salinas approach. Critically, the Salinas approach makes use of the particular layout of the prime, hence the way we depicted P384 earlier. So yeah, it's the OpenSSL default, and it works for any choice of modulus. it uses what's called a field homeomorphism, which means that you map your numbers a by multiplying them by some number r. We pick an r which is cheap to multiply by, say a power of 2, and then we do arithmetic in this homeomorphism, in this mapping of our numbers, which requires a pre-computation step in order to set up this mapping. But once we've established the mapping, then we can do fast repeat multiplication, exponentiation in our field. And at each step, there's a clever trick for reducing modulo our prime, which is cool. But the whole upshot of part of the upshot of elliptic curve crypto over RSA is that the modulus, the prime, doesn't change for a particular curve. So yep, all the arithmetic happens in some fp. That p is a constant, and so because these algorithms are dependent on everywhere now, we may as well then specialize for a particular choice of prime. And so for SecP384R1, what produced such stellar performance for us was using what's called a Salinas method. And so we might be familiar with a Mersenne prime. It's a big number theoretic concept, and it has one particular application in that, usually modular arithmetic with a modulus anything other than a power of 2 is going to be horribly expensive on a computer. But we can we can do it in a computationally tractable way. So suppose our p, our modulus, is equal to 2 to the power n. 2 to the power n, by the way, I'm going to call our natural modulus. So it's easy to do modulo a power of 2 because that's just a bit mask, basically. And so because p is a multiple of p, we say that this has the same remainder as 0. This has remainder 0 mod p. And then treating this equivalent operator here, this congruent operator, as equals, essentially, we can rearrange so that our natural modulus is now equivalent to 1. It has the same remainder as 1 mod p. What does that mean? So suppose we've decomposed a number into x plus 2 to the ny. That's easy enough to do, right? Because how do you get y? You just mask out all but the highest, the 2 to the n place value and higher bits of a number, and then x is just the low order bits of the number. And because 2 to the n can now be substituted for 1, this number x plus 2 to the ny is now just congruent to the sum of its low bits and high bits, mod p. So that's extremely straightforward, and invariably you're going to get a smaller number through this, right? So we are effectively reducing modulo p quite elegantly. Erase slide, erase ink, great. Now there is a more generalized case of Mersenne primes, and here's a bit of a hand-wavy definition for it. So generalized Mersenne primes, we're going to think in polynomials now. So basically they have a particular form. So right here, the prime can be described as a sort of polynomial in 2 to the power n. So let's have a look at that. So p is equal to 2 to the n raised to the m for Mike, minus some delta of 2 to the n. You'll see that how Mersenne primes are also examples of generalized Mersenne primes, because in the Mersenne prime example, our delta is just 1. It's always just 1. But using the same technique, what do we have? This is congruent to 0 mod p. Why? Because we said that it was equal to p, and p is a multiple of p. And so treating this equivalent sign as equality and rearranging, we get that our natural modulus, 2 to the mn, is now congruent to delta of 2 to the n. Alright, so under the assumptions that our delta is not too complicated and not too big, then what we've got here is a reduction rule, a way to efficiently do modular reduction. We do, like last time, we reduce the number into n, x, and y. Y is the high order bits, x is the low order bits, and we just sum x with a scaled version of y. Yes, and we can probably circumvent doing a multiplication here if we're clever, because notice that this delta is a polynomial in a power of 2. Multiplying by a power of 2 implies scaling only. So let's see what we can do with this. So here's our prime. Don't be perturbed. It's a fairly complicated one, but let's try and come up with a polynomial. So if we choose delta t as the following, then it so happens that P384 is then equal to our natural modulus, which is 2 to the 384, minus delta evaluated at 2 to the 32. So what we're saying is that P384 is actually just a polynomial, which is our natural modulus minus a low order polynomial in 2 to the 32. 2 to the 32 actually divides 384. So 2 to the 384 can be understood as 2 to the 32 itself raised to the power of 12. There we go. Yeah, and so using the same logic as last, we have this reduction rule here. So the place value, the natural modulus, can be expressed as this delta. Now what do we do here? Okay, so returning to the idea of limbs. So I described them earlier as sort of digits. But yeah, you can think of base 10 numbers. So here's a base 10 number, 384. This is our hundreds. This is our hundredths digit. This is our tens digit. And this is our units digit. You can actually deem this number to be a sort of polynomial in 10. It feels weird to use 10 as a variable as it were, but there's some things become simpler. So the long multiplication algorithm, for example, which we learned in high school, can be thought of as polynomial long multiplication. Have I just taken a simple concept from primary school and made it more complex? Possibly, but bear with me. So yeah, we've got some number a, and if a is a number which is roughly 384 bits, then we'll want to store it as a polynomial in terms of t, at choice of t. Remember, the t we picked earlier was 2 to the power 32. And so what are these coefficients here? Well, actually they're the limbs which we're going to store. Nice. Now, as per the base 10 example, you do know that, t to the power n, you can think of that as million, 100,000, 10,000, 1,000, etc. These are clearly linearly dependent numbers, right? 10 thousandths gives you a 10,000th. And so this polynomial notation is actually only unique where the coefficients themselves are less than t. And so here's a problem. So suppose we add two polynomials. What we're going to want to do then is add t to the I terms like for like. So we add a and b with coefficients ai and bi. We're going to want to add each ai, bi. But in principle, our limbs, our coefficients, could wind up being greater than t. And we want to allow that for the sake of computational efficiency. And so we actually drop this uniqueness requirement. We allow for some redundancy. That is, we allow for our coefficients to be larger than t, and so all of a sudden there are, finitely many, but still a large number of distinct ways to represent the same number. So let's put this all together. Sorry for the wall of text. All right, so we have some delta here, which encompasses all these terms. It's the difference between P384, the positive difference between P384 and our natural modulus, 2 to the 384. I'm going to henceforth think of 2 to the 32 as just a pronumeral t. And so what do we get? We get that our prime is congruent to t to the power 12 minus our delta. And so suppose we've just multiplied together two numbers. So let's go, d of t is equal to t to the power 11. E of t is 2t to the power 11. Then, as you can tell, they can have a product, which is itself a polynomial with degree 22 here, for example. And so, suppose we have the product of such a multiplication. Sorry, that's d times e. Suppose we have a product of such a multiplication, call it a. Then what we might want to do in order to reduce a, modulo r prime, is separate it out into an x, that is the low order bits, and a y. So y times its place value, which is 2 to the 12, is this polynomial here, c23, c12, etc. And so, as we can see, this is a decomposition for a. And then what do we do? So we substitute t to the 12 for delta. Another way we can think of it is because t to the 12 is congruent to delta, it means it's congruent to this very low order polynomial here. And so what we're doing is we're taking the C12 coefficient, that is lim 12, which is the thing which has place value t to the 12. We're taking lim 12 and then we're multiplying it by this polynomial, which means that we're taking four copies of it. We're adding into lim 4, we're adding into lim 3, we're subtracting into lim 1, and we're adding into lim 0. And so if we multiply this whole equation by t, then equivalence modulo p holds. We now have a substitution rule for t to the power 13. And it's nonetheless in terms of a smaller polynomial. Again, we take lim 13 and we add a copy of it into t to the 5th, we add a copy of it into t to the 4th, we subtract a copy into t squared, we add a copy into t. Yeah, there's a lot of details here, but in short, the real paraphrase here is that even though we're adding a lot of different copies of a lim, we're nonetheless swapping our high limbs, our high place value limbs, for low place value limbs. The actual limbs, as we accumulate these values into our output, the limbs, we're going to introduce some redundancy here. The limbs themselves might get larger, but the numbers which they represent are going to get smaller, because we're going to have fewer limbs in the result. And so we have successfully reduced modulo our prime. Now, earlier we made a choice to set t, which is the bound variable in our polynomial, to set t to 2 to the 32. What that means is you've picked a lim width of 32. Remember, we can't have a lim width of 64, because although we have a 128-bit type on our system, if we want to multiply two 64-bit numbers and then add something, then we're out of bits, because we only have 128-bit types, only 128-bit registers. So why wouldn't I choose t to the 32? Well, t to the 32 is an alright choice. So for starters, it divides all of the exponents in our prime, in the way our prime is represented. And so the maths becomes very clean this way, as it's about to get a whole bunch dirtier. Also, 32 is itself a multiple of 8, which means that every part of our limbs is byte addressable, which is nice. Which means that a whole bunch of micro-ops in assembly, which I ended up doing, worked out quite fast, which was nice. Sorry, proceed. Why might we not use 32-bit types? So yeah, as we discussed, the product of two 32-bit numbers is 64-bit, which means that if we want to do our sums in 64-bit, there's no redundancy. And it feels like promotion to 128 bits then, in order to do an additional addition, just feels too wasteful. And so this motivates the compromise candidate, which is t is 2 to the 56. One thing which you'll notice about the number 384, it is very much not divisible by 56. So that would mean it would have to be divisible by 7, which it is not. Yes, why would we pick t equals 2 to the 56? Well, 56 is however divisible by 8, so its parts are byte addressable, tick. The product of two 56-bit numbers, what's 2 times 56? It's 112. So the products are themselves 112-bit numbers. If we promote into 128-bit registers, by the way, this is something which you can do in GCC. There's a 128-bit type, but it is a compiler extension. But oh well, we're all using GCC anyway, aren't we? So that's not a problem. But yes, now that we have some redundancy in our 128-bit type, then we can do some additions and subtractions without risk of overflow, which is nice. It should be noted, in order for the additions and subtractions to be fast, it helps to also in your architecture have a 128-bit number type. Just because you have vector registers which are 128 bits in length doesn't necessarily mean that you can work with numbers which are 128 bits, integers which are 128 bits. So yeah, seems to be the right amount of redundancy. And so sadly, because 56 doesn't divide any of the exponents involved in the way our prime is represented, we run into the problem where our natural modulus is now no longer a power of our radix here, 2 to the power 56, and so the maths from here on out starts looking a bit funky. So we pick a delta t. I'm sort of zipping through at the moment, but we pick a delta t which has some coefficients of its own, basically, some non-1 or -1 coefficients. But that's fine. So this is a coefficient here. This is a coefficient, and delta itself is an order 2 polynomial, which means that we've got to do basically 3 accumulations with every reduction step. Yes, this is our resulting expression for P384. And so once we do the equivalence, we see that our natural modulus is equal to delta t as such. Okay, right, so we said that our natural modulus, which is a scaling of t to the power 6, is now congruent to this delta. So what do we actually do with this substitution rule? So because this is only a true statement about 2 to the power 48 times t6, what this means is that we have a reduction rule for the high order bits of lim6. So that seems confusing. So only the bits in lim6 which have place value 2 to the 48 or more have this substitution rule. But remember, the t's and their powers are not linearly independent, which is to say that 2 to the power 48 t6, if we were to just multiply it by 2 to the power 8, then we would get t7. And so that's exactly what we're about to do here. So we get a whole bunch more reduction rules once we do that. Erase. And so now we can actually erase lim7. So for the majority of the code, this is what we're doing. We're erasing lim7 by substituting it with a scaled copy, which we sum into lim2, scale up by 2 to the power 24, scale up by 2 to the power 48, sum into lim1, and then scale up by this number and sum into lim0. And then again, multiplying by t, we get the following substitution rules. This all looks pretty nasty, and I'm definitely proving how uninterpretable crypto code can be here. So straight off the bat, we have a whole bunch of random constants. This is what's necessary in order for subtraction to be possible. But yeah, this is the method which does modular reduction, and I'm hiding some of it. But ostensibly, it's this multiple 100-line behemoth, which takes a high input lim. We ultimately want to reduce into just 7 limbs, and so it takes a high input lim, like int10, and then it bit shifts it and it bit masks it and it does some horrible stuff. Int10 is meant to sum into lim5 of the output, but the scaled version of lim10, because if we go back to the rule, for lim10, sorry, one sec. If we go back to the rule for lim10, we actually see that we're going to have to scale by 2 to the 24 before we sum into lim5. And so our code here, it does that left shift by 24, but it can only probably fit so much into ACK5, into lim5 of the output, which is a 128-bit type. And so what it's going to have to do is it's going to have to scatter that number among lim5 and lim6. Yeah, so there's a whole bunch of that. This can very much be put into a loop, but I thought I would unroll it for reasons, I suppose. And then we have to do a whole bunch of carries in order to get our number into the right format, because now one implementation detail here is that in order for, so I said that the limbs are going to be stored redundantly. That is, the radix is 2 to the 56, but I'm allowing for each limb to be potentially larger than 2 to the 56. And so in order to defer reductions until enough arithmetic has occurred, and in order to make our algorithm fast, I need to make sure that there is at least some necessary precondition on the limbs of the input, such that this arithmetic still works without the possibility of overflowing. And so statically, we've got to be able to prove, in order to call this function, that your limbs are smaller than this sum, because of some voodoo magic I do later. And if all those things are true, then we're going to reduce your number so that it's at most a factor of 2 larger than the prime. At most a factor of 2 larger, so that we're actually not going to fully reduce the numbers here, right? So one cool thing about modular arithmetic is that irrespective of how much you reduce the numbers. Basically, two numbers which have the same remainder modulo r prime have identical algebraic properties to one another in modular arithmetic, and so we need not reduce the whole way. Yeah, there's so many dragons in this code, and I hope I've just justified that to you, and I suspect I have. So basically, we've got a 6.6x speed up with this algorithm, and this is a whole new translation unit I put into OpenSSL. Thankfully, it's not groundbreaking new. Like, there are other Salinas implementations, and I borrowed and modified a lot of the code there for adjacent ones which had been written by Google people. But nonetheless, I added 2,000 new lines into OpenSSL, which is pretty horrific, and they were largely accepted without major comment. There's still a lot of comments about my code quality and stuff like that. But this is still 2,000 new lines of code, completely re-implementing and reimagining what's meant to be a standard algorithm according to the NSA. So it is a bit scary just what can get accepted upstream. So the main point of contention was, what are these random constants doing there? And look, that is due diligence. People should absolutely ask when there are random constants, right? The reason why they're here is that this is what's called a telescopic sum. This is a large number whose limbs are all redundant, so they're larger than our radix to the 56, and they all have large limbs, but they sum in such a way so that a lot of the limbs cancel out. So basically, what we're doing here is we're going to take our accumulators and we're going to sum in effect, sum in a large multiple of our prime, so that later when we do these subtractions can never underflow. And where did this number come from? Well, answer, I made it up, basically. So you would understand that the global community, which cares about keeping their data safe, might be a bit concerned about a bunch of random constants. Yeah, well, yes, this is the review, the response to the review requesting me explain these random constants, and then I just tapped this out on my phone while holidaying in the NT, which was good fun. But they did actually catch a trivial but potentially very substantial bug, which is that in basically the absolute minimum amount of memory management which I did, I still managed to do a double free, which is pretty embarrassing. So that's great, but there really wasn't an algorithmic review, and that is a touch terrifying, right? 2,000 lines of new code going into what is meant to be an essential crypto algorithm, and no algorithmic review. That's not true, actually. So they said that they said that they would get someone on the committee to review the specific mathematics, but I didn't see any response, and GitHub didn't show me a tick, so that they had completed the review or anything. So yeah, that's that. Bit of a cautionary tale before we finish up. So there is this assumption, right, that, and you've probably seen this one, there is this assumption that in the open source community, every bit of software goes through 1,000 eyes, and so there's no need to worry about it, right? No, not that, but surely it's much better than proprietary code where the only eyes that can see something in the company are necessarily internal to that company. You have this kind of, sea of reviewers, which is the general community and all the stakeholders for that software, etc. Well, just, a couple of weeks ago, right, there was this XZ backdoor, which ended up backdooring a lot of people's SSH servers. And how was it accepted? Well, because the submitter had gained a great deal of credibility in the project, he had just managed to submit some binary blobs with some obfuscated code, which just so happened to serve as a backdoor into the sort of programs which linked in XZ, and one of them is your SSH server. And so that got in with a looks good to me. That's pretty scary. That's been my talk, really. I think my upshot from doing all this is just to know that while there are a relatively small handful of truly infrastructural projects, like OpenSSL, right? The internet is built upon OpenSSL. You can say that with a great deal of confidence. But while they appear to be scrutinized in every different way, OpenSSL produces a lot of CVEs, and that, I think, speaks as a testament to their ability to responsibly handle with vulnerabilities and their desire to disclose them as soon as possible. These projects, nonetheless, are composed of code, and code might be difficult to crack, but not impossibly so. Essentially, I started out just believing that I could optimize in assembly that multiplication routine, which I showed you, and then I worked on to see how you could make industry-grade encryption out of that. These projects, while they're composed of code which might be difficult to find vulnerabilities in, they're not impossible. Essentially, the motivation for me doing what I did here is that I thought I could get some good performance out of getting this multiplication ladder and then implementing some fast arithmetic around it, and then putting industry, getting my code up to an industry grade with the right caveats like efficient reduction, etc. Loads of other developers come in with the same or similar ambition. We just might not have the privilege of seeing their working. Just because a piece of code can be as complicated as OpenSSL doesn't mean that there isn't room for improvement or additional room for scrutiny. And just because this code might be visible by 1,000 eyes doesn't mean that the invitation to ask seemingly dumb questions is effectively communicated. So an ideal thing in my mind for you all to take away would be a greater enthusiasm for not just hacking on open source projects, but actually asking interesting questions about why things are the way they are. Because chances are it could well be an oversight, or perhaps the maintainer's running out of time, etc. Thank you so much for attending my talk, and I wish you all a great remainder of the conference.